Good evening, guys. Hope you're doing well. We're going to finish our conversation about the laws of Thermo tonight. And then we will move on to our final topic, which is free energy. So let us go ahead and share. We will then start our slideshow. And let's talk about our agenda. So we're going to talk about calorimetry and standard enthalpy of formation and reaction. And then we'll talk about phase changes. So we're going to be talking specifically about what enthalpy does and how we use those measurements, the calculations that we can do with this. So we'll be talking a little bit in specific detail about that. Okay. So let us move to our comments. Questions, comments, problems. Hopefully not, but you know the drill. If you do, please let me know. I'm more than happy to help in any way that I can. So we need to talk about calorimetry in the sense that you guys are expected to do this in the laboratory. It's one of the things that you guys are expected to do for the lab. Calorimetry is a way for us to look at how much energy is transferred while doing a particular thing. So we can talk about the specific heat. That's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree. Okay. We can talk about the heat capacity, which is the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree. Okay. So if we want to talk about 1 gram, that's specific heat. If we want to talk about how, for any other quantity, that's the heat capacity. Okay. We can talk about constant volume calorimetry. That's the heat of combustion reactions that we can look at, which can be measured in a machine like the one above, which is called a bomb calorimeter. Okay. Since in a closed system, constant volume, the change in heat, the Q for the system, is an indicator of the energy of the reaction, Q reaction. Using Q system equals the Q for the calorimeter plus the Q for the reaction. Q of the calorimeter is the specific heat capacity of the calorimeter, which can be measured experimentally using something like this equation, QCal equals Ccal times delta T, where Ccal equals Qcal over delta T. If we work with material with a known heat of combustion, such as 1 gram of benzoic acid equal to 26.42 kilojoules, and measure the temperature change in that calorimeter, we can solve for the Ccal. Okay, so that's something that we do. Now that is a measure of delta U, not delta H. Okay. We can also work with constant pressure calorimetry, such as what we have here. So in the laboratory, we often work with what we call brain has failed. Styrofoam cup calorimeters. This can be used to measure the heat of reaction for non-combustion reactions. Okay, since this is constant pressure, then the Q for the reaction equals the delta H. Qcal equals 0 for calorimeters for like this with 2 stacked styrofoam cups. So we can ignore it. We can measure it if we want to as well. The specific heat capacity of an added component can be determined using a method similar to example 6.7. Okay. The heat of reaction can be determined using a method similar to example 6.8. I figured since those details were in your textbook, I wasn't going to include them here. What you would do is put a specific amount of material into this, measure the change in the temperature, and then use those calculations to be able to figure out what the enthalpy is for those particular components. Okay. Again, we will work with doing some sample calculations with this when I get that sample put together for you guys, but it will be similar to what you see with the examples 6.7 and 6.8. Okay. questions, comments, problems? Hopefully not. I'm sure you probably don't at this point, but you may eventually. And if you do, please let me know. We talk about the standard enthalpy of formation. So we're talking about enthalpy, delta H, it's standard, so 0, and formation, F. So we have change in enthalpy, standard, formation. Enthalpy of formation of a material in its standard state. Standard state means 1 atmosphere, and formation refers to the element in its most stable form. For that state, the formation energy for any material is 0. All other enthalpies can be measured against that standard. So O2 gas at 1 atmosphere at 25 degrees C has a delta H dot F equal to 0 because that's the most stable form. O3 gas at 1 atmosphere at 25 degrees C has a delta H dot F of 142.2 kilojoules per mole. So based on that idea, the standard enthalpy of formation is the heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atmosphere. Those values can be tabulated and are shown in the exam handouts on page 9, table 6.4. We can use the standard enthalpy values to determine the enthalpy of formation of any other material using the following equation. The sum of the number of moles of delta H naught F for the products minus the sum times the number of moles of the delta H naught F for the reactants, where N and M are the stoichiometric coefficients of each species. And I think it's not delta. I think that's sigma, is the sum of the enthalpy for all reactants or products. Okay, so again, it's the sum of those materials. All right. So that's our general thought. Now, this can either be done into one of 2 ways. There's a direct method and an indirect method. So using the direct method, this is used when material is made directly from elements in their standard states. Synthesis of carbon dioxide from carbon, graphite, and oxygen, O2 gas. Delta H naught reaction equals delta H naught F for CO2 gas minus delta H naught F for C graphite plus delta H naught F for O2 gas equals negative 393.5 kilojoules per mole. So since both of these are in their stable forms, those are both 0. And so the only thing you have is the delta H naught F for CO2. So note that the enthalpies of formation for C graphite and C and O2 are 0, since those are the most stable form. And those values are in table 6.4 in your exam handouts. And your indirect method is used when a material is not made directly from elements in their standard states. This uses Hess's law. When reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. That's what Hess's law states. So as long as we can break the reaction down into smaller reactions that have measurable delta H standard reaction values, we can use these values to determine the enthalpy of our overall reaction. Desire to know the enthalpy for C graphite plus half of an O2 going to CO? However, this reaction also produces CO2, so we can't do it directly. We're going to have to do it indirectly. All right? And we can do that by using the following equations to determine the enthalpy. So C graphite plus O2 goes to CO2. We just talked about that formation. We can talk about CO gas plus half of an O2 going to CO2. Okay, and the delta H naught reaction for that is negative 283.0 kilojoules per mole. If you reverse the second reaction so that you have CO2 on both sides, you get CO2 going to CO plus half of an O2, that delta H naught reaction equals plus 283 kilojoules per mole. We then add that reversed equation to the first one with our delta H values here. The C graphite plus O2 going to CO2. CO2 goes to CO plus half of an O2. Then we end up with C graphite plus half of an O2 goes to CO. We add those two delta H values together, and that gives us negative 110.5. So here we have the graphite plus O2 going to CO2, right? And that's negative 393.5. We have our here CO plus half of an O2 going to CO2, and that's negative 283. So the difference between those two is a negative 110.5, which is what we're talking about right here. Okay, so that's how that works. As long as we can get a net reaction that equals what we're looking for, we can use other reactions to help us break down that heat. All right, so that's our indirect method. So we use the direct method whenever we can, but if we can't, we can use our indirect method to do it. So for the exams, both the direct and indirect method for determining delta H dot reaction may be used. Tabulated values can be used to do this. You will be expected to know that the most stable form has a delta H dot F of 0. And that means you should know what the most stable form of a compound is. Common things that you need to know: O2, N2, H2, F2, Cl2, Br2, I2 are all gases, and C graphite. Okay? You may note that these things appear in table 6.4 as 0 values. So you need to be able to explain that the 0 is because it's the most stable form and therefore defined as 0. Okay, so I may say to you, hey, what's the value for this? And give you one of those stable forms. And you go look it up and you write it down. And I say, okay, why is it that value? And you should be able to explain to me that it is that particular value because that is the most stable form. Okay? So that's the kind of question that you may be able to see is, what is the value for this particular thing? And based on that value, what do you know about that particular thing? Okay? Questions, comments, problems about that? All right. Hopefully not, but you know what the deal is if you do. The next thing we're going to talk about is phase change. Okay, so we've talked about phase changes in the past, what they mean, changing from one physical phase to another. Now we're going to look at the enthalpy of these phase changes. So we can talk about the molar heat of vaporization and boiling point, which is delta H dot vape, or delta H vape. The energy required to vaporize 1 mole of a liquid. And that's equal, that has this form. ln P equals negative delta H vape over R times 1 over T plus C. P is the vapor pressure, R is the gas constant, C is the constant. We can plot ln of P versus 1 over T. The slope of the line changes based on the strength of molecular interactions between the molecules. Larger slope means higher intermolecular interactions. Higher heats of vaporization mean higher temperatures at the boiling point. All right, so you may get asked, look at this plot, you have two things on it. What do you know about this thing compared to the other thing? Whichever one has the higher slope, you know that there are higher intermolecular interactions there. You would know that it has a higher temperature at the boiling point based on heat of vaporization, those kinds of things. So that's what I would expect from that. We can talk about the molar heat of fusion and the melting point. Energy required to melt 1 mole of a solid. Delta H vape is always higher than the delta H fuse. Okay, so vaporization is always higher than fusion. We can talk about the molar heat of sublimation. And that's the energy required to take 1 mole of solid directly to the gas phase. So what we can look at is if we go from solid to liquid, that's melting, right? And so that has this particular energy right here. If we go from liquid to gas, that's a vaporization or the reverse condensation. But if we want to go from solid to gas or reverse, that's the sum of those two. That's all you're looking at there. And you may get asked about that. If I have this value for the delta H dot fusion, and I have this value for the delta H vaporization, what's the value for the delta H sublimation? You may get asked, how do you know that those two things give you that sum? And so you need to be able to explain to me how you know that the solid going to the gas is equal to the same as the solid going to the liquid plus the liquid going to the gas. Okay? Questions, comments, problems on that? I'm guessing not at this point. You will get practice for what this is going to look like, how you can do those calculations, what they're going to look like on the test. okay, and how they tie into the other concepts that we've talked about. All right. If you come up with any questions once you've done that, please let me know. That's everything I've got for that particular topic. So that will take us into our, get us ready for our last lecture. So I'm going to stop here, get this uploaded for you guys, and then we will do our last lecture, and then you guys should be ready to go. All right. Talk to you soon.